Okay, so question about tutor. If you Google Javelin College STEM Center, you're going to see this link. You click it, and in there, I was told, so it's in MA 102, they have somebody who has a degree in computer science, supposedly, and the center is open Monday through, Monday to Thursday, 8:30 a.m. to 5 p.m., and then on Friday from 8:30 to 3. So it's a good resource. And on top of this, I'm trying to get somebody to also be like an SI or something for the class, but my normal SI probably won't do. I need someone else who has done this, right? So maybe I'll try to see if I can get the president of the computer science club to do something like this. We'll see. Okay, so yeah, but help's available at the STEM Center. If you don't get help, let me know so that I can see. Student tutors. Yeah, I'm not sure, but I know that there's somebody who's in there, not even the student tutor, there's somebody who works like a supervisor at the STEM Center who has a degree in computer science. That's what Marla Dresch told me, who's the coordinator for the whole thing, the director for the STEM. Okay, so, and by the way, Marla Dresch is the wife of my differential equations professor that I took many years ago. So, small world. Okay, so we are officially in week 3 of the Java data structures, and week 3 talks about the different kinds of sorts. Week 2, had a couple of assignments. The first one was implement a bag of items, right? There's a one that can help you warm up, name.java, but what you really need to do is this thing, that review exercises PDF, right? So we really need to do, I think, steps part 2 or step 3, 4, 5, 6 until the end. Okay, so that's what you got to do. What I did is I posted the solution for this thing. So if you go in there and if you look at week 3, there's a solution right here, and I threw it in Google Docs so you don't copy paste, hopefully, right? And the whole thing is in there. Okay, this is how I did it. You can do it some different ways if you want to do the different parts and different programs and turn in multiple files. That's okay too. I just did the whole thing in one file, one program. Okay. Anyone want me to go over this stuff, or we're good? Sure. Okay. So.
Is it okay?
Huh?
I'm almost done with it.
Uh-huh.
Okay, to look at it and stuff. I'm not
Sure.
going to turn it in, but
Sure.
I've
Of
read
course.
the code.
Yeah. Of course. Yeah. If you get stuck on something, you want to make sure you're doing it right. Of course. Look at it. No problem. Okay.
Close my eyes.
Yeah. If you want to close your eyes and shut your ears, and that way you don't get hints. Okay, so first of all, review exercises. Let me just open up this PDF. All right, so the first thing is it asks to write a Java program to accept a given number of items, item names and prices, then output them in reverse order in which they were input. In addition, output the average price if one of the items is named piece, not case sensitive. Otherwise, output no average output, right? And this is your sample run. Okay, so how did I do this? Looking at this here, the solution. So I have a class called bag, because this is really just, it's a bag, it's an exercise of creating a bag data structure. Okay, so it was asking at some point to create a static method. I'm not sure where's the static method here, but there's a part in there that, is it 5? Yeah, add a static method to the program described above that outputs welcome to Gavilan before the items and prices are output. All right, that's this method right here. Sorry, the welcome, lines 29 through 32. That's my part, I guess not part 2, it's 5. Okay, so it's just a static method, and then you call the static method right here in the main. So on line 55 in the main, you call the static method. Remember, if you have a static method, you do not have to have an object before you can call it. You can just call it the way you see. Okay. Okay. The rest of the parts are basically ask the user to enter a bunch of things. So what I do is I'm using the scanner. Let me maybe zoom in on this a little. There we go. Okay, so I have I'm using scanner, right, to read the numbers in. I'm going to have a variable num items which accepts the user input an integer from the user, and using that num items we create how, you know, the size, you know, do two different arrays. One is names, one is prices, with size num items. Okay, so that's the first step, making these two arrays, and I slightly, you know, changed from how they have it in here. They have it basically one big string. They have the name and the price on the same line, but that would require me to read the whole thing as a string. Then I have to split it by spaces, and then I have to put one into another array, one array, and then the other into another array. So instead of doing it this way, what I did is I asked it for separate inputs, one for the name and one for the price, so on two separate lines. So all it is you have a loop that happens as many times as the user wanted to, right? So if the user wants to insert five things, that's num items, then this loop is going to happen 5 times. That's the value of num items. The value of I changes from 0 to 4, right? That's the standard array business. I asked for the user to enter their name. I used the next method from the scanner class to read a word, and then I put that thing into my names array, which is string, right? Array of strings. And then underneath it I have another question to enter the price. I read the price as a double, and I put the price into the prices array, and that's it. So I read all the input, and the next thing is I have and you can do this whatever way you want, but I have a loop that happens. Oh yeah, this is in reverse, right? So what I'm doing is I have a loop that starts at the last element or the last index. The last index of 5 things is 4, right? So if you have num items is 5, the last index is 4. Why? Because the first index is 0. It goes 0, 1, 2, 3, 4. That's 5 things. So we're starting at 4. We're going until it's equal to 0, and we're going backwards. That's the minus minus. And then I show you each of these names and prices in reverse order. As I am doing this, I take the opportunity to use this loop to find the sum of all the prices and to look. This is on line 84. I'm looking for piece. And because it said it doesn't have to be case sensitive, I use equals ignore case. I mentioned before that you cannot compare strings in Java using the equal sign. So you can't have one word equals another word. You have to say the first word dot equals and then the second word. So names I is a string, dot equals and then some other string. Okay, if this is true, I'm going to change this variable called hasPiece to true. So I'm starting Boolean hasPiece as false. Boolean is a data type which is either true or false, right? So I'm starting it as a false. If we find piece, it's equal to true. And here, if we have piece, so if hasPiece is equal to true. So another way to write this is if hasPiece equals true, right? But this is just a shorthand notation. Then I show you the actual average of the prices, right? And what's the average? The sum, which I calculate in this loop here on line 83, divided by prices.length. Length is a built-in property of the arrays in Java, which allow you to see how many things are in the array. So that calculates the average. And question?
A quick question. On line 88, if hasPiece equals true,
yeah.
No, I got it, never mind.
Got it?
Yeah.
Okay. So again, this is just another way to write has piece equals true.
When you said equals, it kind of threw me because I looked at has piece as a string, and you say equals,
No, has
equals.
piece is a boolean. Line
It's a
70,
variable, right?
line 77, it's boolean.
Yeah.
That's why I can just use this.
All right.
Yeah, it's not a string. Okay, so then I find the price, the price, and then after that it asks at one point, I don't know, sure which part of this exercise it is. There, modified your program so the average price is calculated by a separate static method and returned to the invoker. So that's what I do here on line 92 or 92 and 93. I do the same thing that I did on lines 88 and 89, but using a method. And it's a static method, right? So I'll go back up. Where's the averages? There it is, right? So what I'm doing is I'm sending the array of the prices in. I'm calculating the sum, and I return the same calculation basically that I did in my main. Okay, so it's basically same exact thing, but one is done inside of the in the average method. I do this stuff that I did in this for loop here. So the for loop that's in lines 80 through 86 is what I do in the average method. Okay, and that's it. Now the next part of the exercise tells you, okay, at this point we have, notice here we have two different arrays. One is called names, one is called prices. And they're parallel arrays. They're both equal in size and length. But that kind of makes things a little bit not very efficient, or I guess it doesn't bundle up all the data into one entity. And then the next step in part 3 tells you, okay, well now let's make a new object called item. And in that item object, we're going to have the name of the thing that's going to be in my bag and the price. Okay, so let's say we have milk and then some price. So they're both connected. And how do I do this? I go in there and I make an item class. This is my class item. It has a name and it has a price. Okay, I have a constructor which allows me to set the initial name and price. I have, just like any class, should have accessor methods which allow you to get the variables and show the variables, right? So the accessors and the mutators are there, right? And I also have a little, on line 17, I have a public string toString, right? Which allows you to override how the object itself shows itself. Okay, so it's basically a quick way to show both the name and the price for every item. Okay, so those are my methods. And it's a tiny little class. It's not very long, right? So it goes from line 4 to line 20, so 16 lines of code. Not very long, not very complicated. Okay, so then what we're going to do is, going back to my main, what we're going to do is first I'm testing it out. So before I do anything, do anything fancier, I make on line 98 a new item. I'm calling it grapes, and this is the value of grapes, and then I show you system.println. This line 99, notice how I'm showing the object itself. If I say system.println an item, an item calls the toString method, which is this piece right here on line 17, public string toString. This is a built-in method into the Java language which allows you to override how an object shows itself. Okay, if you don't have this written, if you don't have line 17 written, it will just show you some kind of a weird memory address. So if I was trying to do that, if I did not have the toString method on line 17 and I try to show you the item here on line 99, if I try to show an item this way, it will just show some weird memory address. Okay, but you can override that with the toString method. So that's the first, I just tested it. Okay, an item class, I made it, I tested it, it works. Okay, now the next thing is what I'm going to do is I'm going to create an array of items. Okay, and that's basically in essence your bag. Okay, that's the bag. So you have an array of objects. Okay, And what's that array of objects? Well, it's the same size. It's, if we wanted to have 5 things, that's the size of this array. The first thing on line 103, I say item 0 is equal to an item. So this is basically the first object of this array of objects is equal to this object that I created in line 98. Right? So that's one way to make an array, one of these items in the array of items equal to a new object. Otherwise, I do it in line 105. Okay, you have to say items I is equal to new item, names, and prices. Right? And I have a loop that goes from 1 to num items. Why does it go from 1? Because I already used the 0. Right? I did the first one. And then all the other ones are done in lines 104 and 105. Any questions on that?
So you threw away the user's input for the first one?
Yeah, I used the user input from the first one. So I already have,
You threw it away?
so remember in the first part, in lines 66 through 75, I'm asking the user to enter a bunch of names and prices, right? And I'm just going to use those 2 arrays to create my items.
Your item is grapes and value.
Oh, okay, yeah, so I've changed one of them maybe.
The first one.
The first one is different.
Peas is the first one.
Oh, okay.
So you kinda
Yeah, I changed the first one, definitely. Okay, and then after that, I go in there and I say, all right, well, let's just use these arrays that I already have the user enter, the names and the prices to create my items. Okay, which is just an array of item types. Okay, does that make sense?
So
Okay.
if you want to just take the ones that you inputted and not use the one that you inserted.
Then I would make, if I wanted to use everything as was entered by the user, then I wouldn't do line 103, and I'll make my loop start at 0. Yeah? So if I wanted to use exactly the same stuff, I will do this. But the reason I did it this way is to show you that 2 different ways to make an array of objects equal to new objects. Right? So if you have the object already defined, like in line 98, you have an object called an item, then you can say item 0 is equal to that an item. But if you don't have that, then you have to use this new operator. You have to say items, square bracket, whatever number goes in between, is equal to new item, parentheses, and then you're sending over a string and a number. Okay? So the new item, right? So this is the constructor. Just to refresh your memory, the constructor is right here. Right? So lines 9 through 13, all it does is it takes a string and a number, and then we're passing those 2 from the main using that loop. Okay, so then we make an array of objects, and that's lines 104 through 102 through 105. We basically fill up the information into the items. And then on lines 107 through 114, I do similar thing that I did earlier, right? I'm looking for P's, I'm finding the sum. If I find P's, right? If any of my items .get name, right? That's why I had to create a method which returns the name for each of these items, is equal to P's, then I have P's. If I have P's, then I show you the calculation, which is very similar to what I did on line 89, right? 88 and 89 is very similar to what I'm doing on lines 116 and 117. And then just to do the thing with the method, with the static method, I create a method called average items, and I'm sending all of the items. So when I say average items, I'm sending the entire array into the method, right? So items is, remember on line 102, it's an array of objects. When I say average items, I'm sending the entire array into the method, and the method average items is right here, which is actually part of the bag class. Okay, so the bag class itself, there are 2 classes in the same file, right? This is one class, class item. Underneath it, there's a class bag. Okay, and inside the class bag, I have the average items, which takes the items array and then finds the sum and returns the average.
How much of a difference
same. No much of a difference. You just make sure that so whether you have these classes in separate files or in one file, not a huge difference at all.
So if you take the coder bag, class item, and separate it to class item,
It will work the same.
It'll work.
It'll work the same. Yeah. If you grab this class item, lines 44 through 22, and you saved it in item.java, as long as that item.java is saved in the same folder as your bag.java, then the bag is going to have access to the item. And that's why in Java it's important to have like the public and private variables, because the access to different properties of one class can be restricted by making things private.
So it would be public on class item, public on class bag.
Yeah, public. There's also private classes too. You can have private. There's also protected and all kinds of different ones. And I
took your code and separated it, but for some reason we can look at it afterwards.
we can look at it.
It did.
Yeah, it should work the same. Okay, and yeah, that's it. So that's the solution for assignment 1, and that's and a sample run underneath it, and that's your assignment 1. Assignment 2, I haven't posted a solution for it yet because I figured that it will be very similar to the one that you have as an example. So in the book, listing 2.3, there's a high array Java program, and let me see if I can find it. It's not it. There you go. All right, this one fine. There is a method called getMax. All right, so the getMax thing is basically you just go through all the elements and you find the max. Not a very complicated thing. So what is the high array? The high array is we have an array of objects. I mean, sorry, not array of objects. We have an array of integers, right? Long is just a longer integer, and in there we have an integer to tell us how many things are in the array. Okay, when we create a new one, the constructor here takes a max to create an array of size max, and it starts the number of elements at 0. And then every time you insert, let me see if I have an insert. See the insert? Every time you insert a new value, right? N elements is equal to that value. So n elements starts at 0 originally. You insert a value, and then you increase the number of elements by +1. And that's it. Okay? Yeah. Any questions on this stuff? Yeah. Copy what's in the book and then add, I think this one here I added the get. Yes. Yeah, the book I think shows everything except the get max. Yeah. And then yeah, you're supposed to add the get max, but it's not very complicated. All you do is you look for the max using a loop. Okay? If you don't find it, which is kind of weird, you return a -1. That's why max starts at this. So I guess if it's an empty array, if it's a size 0, if you didn't add anything to it, then max will return as a -1. Okay, and then finding things, right? I really like this book because it really goes in crazy amount of detail with comments. Like this guy comments every line of code, which is not very common in a lot of these programming books. And then a lot of times they'll have like these, I mean, and notice like his lines are short. Like everything is like less than like 60, 65, 70 characters wide. So it's a very neatly written code. And a lot of these data structures books, you open it up and it's like the code stretches on the whole page and it's hard to read and there's no comments. Or the comments are all in the beginning and then at the end, and it's good luck figuring it out. So, but anyway, he explains, Lafour explains in detail what's happening in every step. But basically, this loop here goes through the array and looks for a search key, which is the value you're looking for. As soon as you find it, you break, you stop the loop. And the reason we declare this J before the loop is so that we can reuse it. So basically, J starts at 0. As soon as you find what you're looking for, you stop. And then if j is equal to number of elements, that means that you went all the way to the end of the array, you didn't find it, and you return false. And otherwise, you're going to return true, right? So if you can find it, return true, otherwise return false. The delete method is similar, right? You look for it. If you can't find it, you return false. Otherwise, if you found it, you have to shift, right? So you have to basically, let's say if you're found the thing to be on in the first spot, you have to shift the second one to the first spot, the third one to the second spot, the fourth one to the third spot. So you shift all the elements one to the left on top of the deleted one, and then you resize the array. Right? So this is the shift, this is the shift, this is the resize of the array, and this is the return true. And again, it's not really resizing the array as we're really changing the size of the array. What we're doing is we're just changing the variable num elements. Okay, and it's just to illustrate, this is how things work on the on the basic level. Okay, if you want to really resize the thing, you could use a vector, right? Vectors in Java are basically resizable arrays, but we're not going to use them. Okay, and that's the reason why this guy's using arrays. That's why LaFour is using arrays. Okay.
A question on
Yeah.
the insert function.
Yeah.
Would it be good to have a check that you don't go over of your n elements allowed?
Totally. I was thinking about that. Yeah. It would make sense. It would make sense for the insert to have some kind of a check if num elements is less than. Do we have anything else? Max, but we don't know what max is. You can because max is a local variable for the high array method or the constructor. What you can use for the insert is you can say if an elements is less than, what's my array, a dot length. That would make sense, and only then do you do these two lines. Yes, that would make sense. Okay, so that's it. So what do you have to do? You have to do a get max, which is returns the max value, and then there's another one which is to not just get the max, but remove the max. So you already know how to delete. This is your example of how you delete a thing, right? So you can use you can find a max, and as soon as you find a max, then send that value into the delete method, and that takes care of the business. So you can reuse the already built methods to get the job done, or you can write the whole thing from scratch, whatever you want. Okay. And if you want, I'll post a solution for that too. Yeah, just let me know. Okay, so that's it. So that was the assignments 1 and 2. And this is basically your introduction to what did we do. We grabbed an array, we put it in a class, and then we wrote some methods that allow us to insert into the array, and then remove from the array, and then search the array, and then delete from the array, and that kind of stuff. So that's a bag. So we learned about encapsulation, which is putting that array inside of a class, and we learned about the abstract data structure or abstract data type bag, which is a collection of items, not in any particular order. You could have duplicates, and the possible operations for the bag are add, remove, look for, delete, all right, and then list the things that are in the bag. Okay, so that's one type of data structure which is applicable for one type of data type. One type of a real world problem has its own real world or data structures solution. So the abstract data type is the real world problem. Data structures is how we implement it in computer science and programming. Okay, so our code is the data structure. The abstract data type is the real world bag thing. Okay, so now week 3 talks about sorting. Okay, so I'm following this book pretty much word for word, as close as I can, because it's awesome. And there's different sorts. There's different sorting algorithms, and I kind of like these pictures in here so that you can see how it works. The bubble sort is the easiest one. Let me try to reload the page. Maybe it'll restart. No, it doesn't. Whatever. Okay, so basically, wait, did it? No, it doesn't. Okay, so basically the bubble sort is the one that we kind of cover in, I cover it in CSIS45, I cover it in 24, I cover it, I don't remember, do I do it in Python?
Yes.
Bubble sort?
So,
Yeah, we do probably bubble sort in there too. So the bubble sort is the easiest to understand algorithm, okay? And by the way, there's a link here for sorting algorithms, right? You have insertion, selection, bubble, shell, merge, heap, quick, right? So we're gonna do these first three today. These other ones, the shell, the merge, the heap, the quick, they're a little bit more advanced. Later on, I'll show you some of these things. The heap sort is basically once we learn about trees, there's a special kind of a tree which allows you to have the highest or the smallest thing on top. So the sorting algorithm uses that data structures to sort things. There's also shell and merge and the quick sorts. Some of these are actually pretty advanced sorting algorithms. I know one of them was, developed by one of these founding fathers of computer science who got his PhD for writing that algorithm. So don't be surprised if it's not easy to understand, all right? But we'll do the best we can to explain it to you. So anyway, if you play these, if you hit play all, try me, you're gonna see how quick the different sorting algorithms sort through these things. And usually you'll see that the bubble sort is kind of the slowest, okay? Or these first three are kind of slow. Okay, and some of them are good for different arrangements of data, right? If it's partially sorted, if it's really a random, right? Some of them tend to do better than others. And what we're going to talk about today, these three sorting algorithms, is I'll show them to you. I'll tell you a little bit about their efficiency, why one is more efficient than another, and I'll kind of walk you through the program. And that'll do. So, and to visualize things, first of all, the bubble sort is the easiest one, right? And it also happens to be the slowest, right?
Sorry,
Yeah.
What was the link for the?
Right here, on the bottom.
Gotcha. Thank you.
Sorting algorithm graphs shows you that graph. Okay, yeah, you have your solution. Wow, I posted it twice. Grocery checkout Java solution for assignment 1. Man, I actually posted the whole thing. Show items. Delete item. Oh, that's the solution for assignment 2. So I don't. Yeah. So solution for assignment 1 is this. Solution for assignment 2 is this. I gotta go double check that I'm correct, but yeah, those are the two solutions for previous week. Okay. Insert in order, right? I'll go over that in a minute, but let's have a look at lecture 3, which is from chapter 3 of the textbook. Okay. So, looking at this, and I'm a huge fan of LaFour. I love how he explains things, right? So we have an illustration here with just a bunch of, it's a baseball or whatever team, people with random sizes, right? They're not in any particular order, and what we're trying to do is we're trying to sort them in this kind of a way, okay? And what he tells you is that as a human being, you can just kind of eyeball the thing and eyeball a solution also. That's why we're kind of not really we don't really think algorithmically in our real life. You don't go, okay, step 1, I got to do this. Step 2, I got to do this. You just kind of come up with a solution all at once. Okay, but the computer can't really do that. So the computer can kind of only focus on two things at the same time, right? Because of the ALU in the processor, the arithmetic logic unit. can only compare two numbers at the time, right? So is this one equal to this one? Is this one less one than the other one? So the computer is restricted to only looking at two of these players at the same time. And we're gonna have to figure a way to, you know, trick it into, you know, doing all the operations we need. So the way we're going to do is so this is basically we're going to compare two items, and we're going to be swapping their places or copying places from, you know, copying one to another place, that kind of things. Okay, so I already told you the bubble sort is notoriously slow, but it is conceptually the simplest one of the sorting algorithms. Okay, and it goes like this. You have two players that are next to each other, okay, and if the one on the left is taller, swap them, and then move over to the next two players. Okay, so if you look at this little picture in here, that's what's happening, right? Is this one bigger than this one? Is 6 bigger than 2? Yup, swap their values. Okay, as soon as you're done swapping, then move over to the next two. Is 6 bigger than 4? Yes, it is. Swap their values. Then, as soon as that is done, when we get to this one, we resume from the beginning, right? So is this one bigger than this one? No. Go to the next one. Is 5 bigger than 2? Yes. Swap. Move, you know, then move over to the next two. Is 5 bigger than 4? Yes. Swap, right? And if you do this repeatedly over and over and over, you're going to end up, you know, sorting the whole thing. That's the bubble sort. And let me have a look at the, you know, the little illustration here, and that's what he shows you. That's what LaForce shows you with this illustration. Okay, and it talks about invariance. In many algorithms, there are conditions that remain unchanged as the algorithm proceeds. These are called the invariants. Okay, in the bubble sort program, the invariant is that the data items to the right of out are sorted. So you have this is his bubble sort. Okay, and it is a little bit more. It is a little bit more efficient than my bubble sort that I showed you in the 24 and the 45. And in my sorting algorithm, I kind of told it, go all the way to the end every time, right? So basically, in the sorting algorithm that I showed you, you know, once you move the biggest number to the right, you go back to the beginning, and then you repeat the process, and you go all the way to the right again. Okay, but you don't have to go all the way to the right. You could stop at the last one, at one before the last one. Once you have done it one time, you don't have to go all the way to the end, because the last one is already sorted. It's already been moved all the way at the end. Okay, and that's how he improves the algorithm, by basically starting this thing and stopping this thing at the one that's already been sorted. Okay, so all it is we have two loops. We have one loop, another loop, an if, and a swap. Okay, and it helps if you write your swap method. You don't have to have a separate swap method. You could swap right in there, but it looks neater if you do. Right. So what is this? Compare two elements. Is if the left is bigger than the right, swap their values. Okay. This loop is so that you can go through all of the items grouped by two. So if you basically, this loop is so that you can change the value of in. Okay, and how far this loop goes is based on the value of this loop. Okay, so the top loop repeats the inner loop. The inner loop is only to change the value of in. Okay, and again, the value of in starts at 0 and stops at out. Out is originally as big as the number of elements, okay, but then it starts decreasing itself every time, because you don't have to go all the way to the end, right? So once you have moved the biggest number all the way at the last place, you no longer have to go to the last place again. You could stop at one before the last place. Once you grab the second biggest number, and move it to the second to last place from the right, then you no longer have to go any further than that. So every time you stop one place in one step less than before, and that's it. Okay, so the efficiency of the bubble sort. Okay, so the bottom line is, if you have 10 items, these are the number of times that you're going to have to do this. First time you have to do it 9 times, then 8 times, then 7 times, then 6 times. As you move every number, however many times the inner loop will have to happen changes. Okay, and if you do this, so you basically have n minus 1 times, n minus 2 times, n minus 3 times. If you summarize this thing, it comes out to be n times n minus 1. Right? Well, if we, for a really big n, we really don't care about that minus 1 that much. So you could kind of reduce this n times n minus 1 to n squared, right? Basically, n times n is n squared divided by 2. And for a really big n, the division by 2 also doesn't matter that much, right? So we can kind of ignore that also and conclude that the efficiency of this algorithm is just n squared. Okay? And if you look at the chapter 2 lecture, I think it was, there was like a graph that shows you the efficiency of the different algorithms. The n squared was the one that kind of grows exponentially. That's the slowest one. And then there's some other ones like the log of n and the linear ones. Okay? The bottom of the story is, whenever you see something that's n squared, that's not very efficient. Okay? And why basically does this happen n squared times? Because you have one loop that happens approximately n times, and another loop which happens approximately n times, even though the author kind of made it more efficient. N times times n times, and then inside of it you have a swap. So you have n squared swaps happening. That's the efficiency of this algorithm, right? So the big O notation for a bubble sort is O(n) squared. Okay, the big O notation is how we measure the efficiency of the different algorithms. Okay, and then it tells you, yeah, whenever you see one loop nested within another, such as those in the bubble sort, right, you can expect that the algorithm is going to be O(n) squared times. Okay, and you will notice that the other selection the selection and the insert algorithms also have a loop inside of another loop. But what happens is we move the swap kind of outside of it, okay? Outside of the inner loop. So the swap doesn't happen n squared times, it happens less. Okay, so what we're doing is, what we're going to do is for the selection now, let's have a look at it. So select sort, what happens is, let me wait for it to go to the end. Okay, so what we're going through is we're starting at the first place, then we go and we look at the smallest thing, and then we swap the first one with the smallest. Okay, then we go to the second thing, we find the second smallest, right? So the first one, find the smallest, swap the first and the smallest. Second one, find the second smallest, swap the second and the second smallest. Third one, find the third smallest, swap the value of the third smallest, etc., etc., etc. Okay, does that make sense? Okay, so how does this work? Yeah, and there's another illustration in there, right? So you're starting in the beginning, you're looking at the minimum, right? We're going to swap the values of this one and the other one, right? Then we go to the next one. If the next one is already the second smallest, maybe you don't need to do a swap, right? Then you go to the third one. Right, you look for the third smallest. This is this one, right? Then you swap this one with the smallest. Okay, etc., 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 until you basically get to the end, and that's the selection sort. Okay, and if you look at the code for the selection sort, it's similar to the other one, right? You have one loop, then you have another loop, right? And basically one loop makes the other loop repeat as many times as you want. What you're doing is you're looking for the index for the minimum one. Okay, when you find the index of the minimum one, so this loop here with the if is just to find the index. Okay, as soon as you find the index of the minimum one, you swap it with the index of out, right? So remember, the out starts at the first one, then you look for the index of the smallest, then as soon as you find the smallest one, you swap out and the minimum. Then you go back, out becomes a 1, right? Now you're at the second one, start from the second one, look for the smallest. When you find the smallest, swap the second one with the smallest. Then you go to the third one, right? You look for the smallest one again, etc., etc., etc. How is this one more efficient than the previous one that we saw? Well, in the previous one, in the bubble sort, notice that the swap is inside of my inner loop. So the swap happens as many times as this loop, okay? But on the other one, in the selection sort, notice where the swap is. The swap is here, okay? So the swap happens less times. So even though we could say that, yeah, this is kind of like an n squared times, you know, it happens n squared times, the swap itself happens less times, and the swapping is something that takes time, all right? Especially if we have like some really big objects. We were talking about integers here, but if you have like some monster object and you're trying to swap this thing with the other thing, there's like, you know, there's a time that takes to swap these big objects, okay? And that's it. So that's basically the efficiency. So the swap is inside of the outer loop, so it happens n times instead of n squared times. So that's the improved efficiency of the selection sort. Okay. Oh, and then by the way, before I go too far, in here I have the basic sorts written for you, which is pretty much what you have in the book. But I kind of added a little bit, a few other things. I think I added like an insert at the end. Is that it? Yeah. I added an insert at the end. This is the swap. We have a show array. Okay, so I added basically a whole bunch of comments about what happens, right? So I kind of expanded the comments of the author to include some more of my own stuff. Okay. And what really helps, or what really, well, the bubble sort is no brainer. It's not very hard to visualize. You compare left to the right, swap, no big deal. Okay, but some of these other ones, it would really help you to basically say, all right, hold on, let me focus on this piece of code here. Okay, how is that going to work? Okay, so let's say I'm going to start with this kind of an array, 2, 4, 1, 3, right? So I'm starting at min index. Min index is equal to out, which is 0 initially, right? So then this thing starts at in is equal to out plus 1, so it starts at 1. So notice we're starting not at 0, we're starting at the one to the left of the one that we're looking at, okay? And then we're looking for whichever one is smallest, right? When we find the smallest, we swap the value, right? So we go through there, we find that this is the smallest. Well, the next step is we're going to swap the values of the 2 and the 1. So it turns out into 1, 4, 2, 3. Then now my min index, which is equal to the out increases by 1. So now the next step is min index is equal to 1. That means that my for loop here starts at 1 plus 1, which is 2. Okay? And then again, we look for the smallest one. Right, we're already at 4, right? So we're at this one. We're looking for the smallest. Which one is the smallest? It's the 2. So when I swap those two, then it's going to go look at. It will look like a 1, 2, 4, 3. Then I repeat this operation again, and then the thing is sorted. Okay, so writing out the code in these little tedious steps for me, it helps a lot. Okay, and it would make, you know, you would read the book and you'll say, oh, this is easy. I got it. This is not that hard. But then when you look at the code, because of how efficient this author is in writing these things, it will take you a little time to understand what's going on. And the best way to understand it is just do what I'm doing, okay? And don't even just, I mean, it's good to look at my example here, but then try to do this for yourself, okay? Go through these individual steps of the sorting algorithm yourself, and you'll understand how it works, okay? So this is my selection sort. Does that make sense? Okay, so that's done. All right, now the next one is the insertion sort. The insertion sort is the most efficient of these two, or of these three, and it also happens to be kind of the most confusing one. Okay, So let's have a look at it. So the insert sort, I'll look at the summary of the book that I have. Okay, so the easiest way to figure out or to understand the insert sort is if you begin with a partially sorted list of players. Okay, so we have on the left, let's say we have some kind of a player which is marked. This is my marked player. To the left of the marked player is we have something that's already sorted. Okay. The next thing we're going to do is we're going to take this marked player out. Okay. And what we're going to do is we're going to figure out where this marked player is supposed to be inserted in this list of already sorted players. Okay? So where are we going to insert this marked player? I don't know. It looks like it's after the one with the hat here. Right? So what are we going to do? We're going to look for the place for this thing to be inserted. Then we're going to shift the other ones to the right and then insert it at the correct place. And then we go to the next player, we look for where that should be inserted, and we insert it in that particular spot. Make sense? Okay. So, if you look at it, this is the actual code of this thing. Okay? And it's a little bit more confusing, but basically all it is again, you have a loop that happens as many times as we have players, and we're starting to look at where to insert this player. Okay. So the invariance of the insertion loop is everything to the left of my marked player is already sorted. Okay, that's the assumption. And the efficiency is kind of sort of pretty much improved because there isn't really swapping, but we're copying a player into one place and then shifting the other ones. Okay, so let me look at, and again, like I said in the beginning, for different data that is arranged in different ways, it makes sense for this to be more efficient, right? If you have something that's already partially sorted, this inner loop, which happens as many times until you find the right place to insert this, is not going to happen that many times. Okay, so let's look at an example of, like, in this little code here. Okay, and then look through all my comments, right? In the outer for loop, out starts at 1, the second element, and moves to the right. Out marks the leftmost unsorted data. Out is the index of the element that is to be inserted in place. In the inner while loop, in starts at out and moves left. Okay, until either temp is smaller than the array element there, or it can't go left any further. Each pass through the while loop shifts another sorted element one space right. Okay, so basically what happens is left of out is a sorted subarray, store element of out and temp. Right, there's a temp in there. Okay, find where the element at out is supposed to go in the above subarray. Shift right all elements to the subarray greater than the element of out, and then insert temp where the value is supposed to go. And the best thing to visualize how this works is the same thing that I did for the one before, especially for this one. Right? You go in there and you start with like a simple array of like 4 things and arrange it in some scrambled order so that it does it every single time. Right? And then look at what happens. So let's say we're starting with 4, 2, 1, 3. In originally is equal to out. Out starts at 1. Okay? And then we do this. Temp is equal to in, so temp is equal to this one. And notice how I write it out. I write out every little baby step. Okay? Then we keep looking, right? We look if in becomes equal to 0, if we get all the way to the left, or if array in minus 1 is bigger than temp. So if basically we're looking at the insert spot. Okay? And then we keep doing this and doing this. So this is, so 4, 2, 1, 3 is the initial step. the initial, then we move the 2 in the beginning, then we go to the second one. Second one is this, actually n is equal to 2, so we go to the third one, okay? We're looking at, this also does a shift, okay? This array n is equal to array n minus 1, okay? What we're doing is we're shifting each of these players, of sorted players, to the right, okay? So remember this. So you basically, we look for where to insert this player. Okay, so the marked player, we're looking for where to insert it, and every time as we go through each of these players, let's say this one here, is this where we're going to insert this one? No. Then move this one to the empty spot. Then we go to the next one. Is this where we're going to insert this one? No. Move it over to the one spot to the right. Then we're going to go to the next one. Then we're going to, is this where this is going to be inserted? No. Move it one to the right. We're not doing swapping because we already took out this player. We took out the marked player, we put it in a temp, and now we're just doing shifting. We're just shifting each of these one to the right, one to the right, one to the right, until we find the correct spot where this one is supposed to be inserted. All the other ones have already been shifted. You put it in the right spot, and that's it. Okay? So the best thing for you to do is go through this, go through all the different steps that I went through these, as I showed you, and check it out for yourself. Any questions? Okay, so read the book, read through my code and the comments that I have. Then what we got to do is a couple of assignments. Insert sort to find median, right? If you don't remember what a median is, it is the middle value. Okay, so if I have an array of 4 things, right? The median is actually the middle 2 values, right? The average of the middle 2 values. Okay? If you have an array of, if you have an array of even number of things, the average is going to be the median is going to be the average of the 2 values in the middle. If you have an array of odd number of things, the median is going to be the value that's in the middle.
But it has to be sorted first.
It has to be sorted first, and that's why you get to use the insert sort. So yeah, use the insert sort to get this thing sorted, and then look for the median. Okay? So not very complicated. I'm not telling you, okay, write the insert sort from scratch, because you're learning about insert sort. Okay? And that's it. So find the median. Not very complicated, especially if you've done my other classes. We do medians in them. Hopefully I've done them. Okay. Then the other one is use insert sort to create no duplicates method. Okay. So how does that work? To the insert sort Java program, add a method called noDups that removes duplicates from previously sorted array without disrupting the order. Okay, so that's kind of, once you have this thing sorted, it makes it easier because you have to just compare the thing to the left and right. You started an index, you started an element of an array, look at the thing of the right to the right of it. Is it the same? If it is, get rid of it. Then once you get rid of it, you do that deleting and shifting thing that we learned already, right? So when you delete an element from an array, you shift all of them that are to the right of it, one to the left, and then you just repeat the operation again. Is the one next to it the same? If it's not the same, move over. Go one to the left. Then repeat that operation again and again and again. Okay? And I'll post the solution for that too when time comes. But not super complicated stuff. Okay, it's just basically get comfortable with these different sorts, understand how they work, and then play around with them a little bit. Questions? Okay, don't get overwhelmed. It takes a long time to get this information sink in. For me, it took a long time too. Okay, so if you feel your brain pulsating, that's normal. Okay? It takes time. And the best thing to do is look through this and work through this the way that I showed you. You start with like some simple array, understand how things move around, okay? And then once you grasp this, once you get it, then the rest of it, finding the median and getting rid of the duplicates, is not that bad. Okay? And that's pretty much all of it. Let me go back to week 1 maybe. No, go back. Previous week 2. In week 2, there's a link here, right, where I illustrate how you do the inserting and sorting things, inserting and deleting things. All right, so this is the shift that I was talking about. If you don't visualize how to delete elements, do what I did here, right? Same thing. I'm starting with an array of, right? I'm just going to start with some super simple array. Let's say I'm trying to delete the 4. If I delete the 4, that means I'm going to have to shift the 3, 1 to the left. I'm going to have to shift the 5, 1 to the left. The first thing I'm going to have to shift is the 3. The second thing that I'm going to have to shift is the 5. I can't shift the 5 first because then I'm going to lose the 3, right? And then I have to resize the array or change my number of elements by -1. And that's it. So this stuff is very important. Understanding how to delete things, how to insert things. Okay, if you forget it, go look at chapter or look at that week that I showed you. Okay? And that is all I have for this week. If you don't have any questions. And if you do, I got office hours right now. And if you can't make the office hours, send me emails and I'll help you out. And that's all I have.